Awesome. So as we said, today is going to be a weekend lecture. So we're going to go a little bit quick on this one. We're not going to go full hour and a half. So we either will take like a longer break or we will take like a shorter lecture as you guys wish. Today's lecture is going to be a pretty easy one. So it's going to be about interpretable machine learning. And the content in general is going to be as follows, right? So we'll first start speaking about things like interpretability and interpretable models. And then we'll speak about one algorithm, which is an amazing algorithm for interpretable machine learning in general. But this one is like a black box model. So it's pretty slow. And then we will see a very fast model for computer vision or a very fast algorithm for interpreting computer vision models, which is GradCam. Before we continue with the lecture, I just wanted to share with you a very important link that I highly recommend everybody at least takes a look at or reads it. And it is called Machine Learning book. Let me just check where it is. I think it's this one. Nope, not this one. Interpretable ML, maybe. Yeah, this one. Yep. Let me share it with you guys on. Yep. So let me just share the screen with you and show you how this book is organized in. I will not recommend a lot of readings. I know everybody hates readings, but if you're one of the few people who actually enjoys reading books, this is like a free book outside, like that is available for everybody. And you can just read through it very quickly. It's easy to understand. It has lots of pictures and everything. Let me just check again if the pictures would load. No, they did not load. This website uses cookies. Okay, got it. Yeah, it has a lot of pretty pictures. I don't know why for now it doesn't load them, but it's pretty easy to read through as you see. Yep. So as you can see, it starts with basically the concept of interpretability and then goes to the importance of interpretability. A lot of examples, especially like real life examples that could be helpful for you guys if you want to go as a career in interpretability for research or even for like companies. And then the evolution and properties and then human-friendly explanations and the importance of having something that is humanly interpretable or humanly readable, because interpretability could go like super crazy and every model will start to provide you with a very long list of explanations why it did what it did. So it's very important to make it very human-friendly and easy to read through. And then he goes through a list of easy to interpret machine learning models, such as linear regression. Obviously, it's very easy to interpret. Logistic regression, and then the other generalized linear models and decision trees and decision rules, rule fit, other interpretable models, naive Bayes, and KNN. And then here, I think this is where things become a little bit more interesting, is when we start speaking about the model agnostic methods, and you will see a very long list in here. One of them is, of course, Lime, which we will see. And then at the end, we will speak. I don't think there is a part here about GradCam, but at least you will have the majority of this lecture if you want to. Oh, here, we have it. Oh, they added it in the new version. So that's amazing. Yeah, so you basically have everything in this book, right? It's a pretty good book for everybody who wants to get started in the field of machine learning or interpretable machine learning. So I highly recommend at least taking a look at it. Or if you are preparing for the exam or for the midterm, I will definitely be asking questions from that book directly. So let's get started. What is interpretability? Why is it important? And what's the scope of interpretability? And then we will go quickly speak about simple models such as decision trees and logistic regressions. So interpretability, first, before going into what it is and how it is done and all the algorithms, just like a small, what is it called? A small reason for why I began in getting interested in this field is when I was investigating the performances of this one is ResNet, I think ResNet 50 or a big ResNet model. And I think any human can easily recognize that this is a horse, right? So a human would not suffer at all at understanding that in this picture we are speaking about a horse. But sadly, even a ResNet 50 that is trained by Microsoft on very large servers and very big amounts of data, their model has predicted that this is an Arabian camel, and it did with a very big, certainty. So it's very confident about what it said. Clearly, this is a mistake. And this kind of mistakes is not just common, for example, if you are building your own data set, for example, if you're in a startup, or if you are just like a small to medium large company building your own models. Of course, these models will be very, very biased towards the data that they were trained on, and they will be making a lot of mistakes. But having this tool of interpretability and the ability to basically model or monitor the model once it is in deployment, it's being run, it's being executed. From time to time, it's very important to look at the model's decisions and try to understand why your model did what it did, right? So it's very important for things, for example, like fairness and making sure that it's not, racist or something like that. And that leads us to the second part of interpretability, which is the importance of interpretability. And here, it's just not about like things, for example, when you're doing it in a lab. It's okay if your model makes like an accuracy of 80% or 88% or something like that. That's completely normal, right? So it's not a big deal. Nobody's going to use the model. It's not going to be making life or death situation, decisions. But for the majority of the models that you will be building, for example, in deployment, let's say a bank or something like that, and you are building the model that, decides basically the fate of whether a person gets a loan from your bank or not, right? This model, of course, its job is to make sure that the bank does not lose any money. But at the same time, if your model is biased towards a certain, category of people, let's say it is biased towards women, or it is biased towards Black people, then that's going to be very harmful for your bank on the long run, because, well, first of all, people are going to like complain, and you're going to get a lot of lawsuits on you. So this is like pretty bad on for the company, and it's also pretty bad for these individuals who have like a very good profile, who are deserving of getting that loan and are trustworthy of basically getting that loan. But just because your model is basically a little bit racist, it's not going to give them the loan, right? So it's pretty important to make sure that your model is not racist, especially if you are not just doing it for fun. If you're doing it for research, also, it's pretty much okay, because nobody's going to use your model in real life. It's just like the idea that you are presenting. But if you are building a model for real life situation or for an industrial company or something like that, you must have this step of, monitoring the model and interpreting its decisions. Some of the reasons that you might have is basically simply satisfying the human curiosity. People are pretty curious about many things. Well, this is not like curiosity, but let's say you are a doctor and you have like a machine learning model that is looking at 3D scans of patients. And for some patients, the model has said, oh, this one has cancer for some reason. So it's very important for you to understand, why did the model say that this person has cancer, or this person has a potential of developing a cancer cells, right? So this one is the satisfying the human curiosity. Improving recommendations. So let's say, for example, I'm sure everybody in here has at least like Facebook or Twitter, or maybe what is it called, Instagram and TikTok, or even Netflix, right? So all of these models, they allow you the ability to press like, right, to like something. And then if you see like a post or a video that you're not interested in, they also allow you to put like, I am not interested in this. Why? And they give you like a couple of reasons why you might not be interested in that, so that you answer them why, and then they learn a little bit better. So in the future, they make better decisions or better recommendations. Another reason could be safety measures. So if your model is something that is trained, or something that is used, for example, for self-driving cars, or something that is responsible for human life, I don't know, some model that is in a big nuclear facility or something like that, that's definitely not something that you could just easily trust. Going back to the first point, which we discussed earlier, so detecting biases against certain minorities, such as Black people or people of color in general, or people of different genders, like women or sometimes even men, right? And basically debugging and auditing your model to find this is something pretty interesting also, especially if you're building something that is industrial. It's important to understand what your model is confusing in terms of classes. So let's say, for example, your model is always confusing something like small dogs with cats for some reason. And for some reason in your training data set, you were training like cats and dogs, and your model only saw big dogs and small cats. So when you were testing it and the model has seen a Chihuahua for the first time, it keeps making the false prediction of this is a cat. So it's important to also interpret your model and understand what are the classes that your model is always, what do we say, confusing between each other, so that you bring more of these classes into your data set, right? So if you notice that the cat or the model is making a big difference, or not making the difference between, as we said, small dogs and normal cats, then it should receive more of these images in order to improve its performances. Definitely in the case of cats and dogs, it's not that important. But in the case of, let's say, a medical issue, and it's confusing something so simple like, I don't know, like a small cough with like COVID, then you're going to need to introduce that new category of, cough, or that new category of pathology into your model so that it understands the differences between them. Now, the scopes of interpretability, there are three major levels, and then there are two local levels of understanding of interpreting interpretabilities, or of performing this interpretability. So the first level is the scope of interpretability. And if we go back quickly to let me just stop sharing and maybe bring that book also here, because it's a pretty interesting book, as we said. Let me close this. I don't know how to use it perfectly, but let's see. Opa. Yes. I think let me share right now. I think this is it. Yeah. So here, if we go back to this book, and again, we look at this concept of scope of interpretability, you will find a lot of extreme explanations, and this will help you a lot to understand it even deeper. But overall, there are, as we said, 5 levels of, or 5 scopes of interpretability that you could perform your interpretability in. The first one is algorithm transparency. And this one is completely unrealistic, mainly because it tells the information of how does the model, or how does the algorithm create the model, right? So if you are, for example, building a research paper that is, open, and everybody has that paper available. So usually you would just give them the code and outsource basically the data set, and everybody can at least run it. They can read the code, they can see how does your model get trained, right? So algorithm transparency allows access to the algorithm itself that trains the model, which is extremely impossible for situations like, for example, you are Facebook or you are YouTube, and your recommender system, everybody's trying to have access to it. You cannot really give that there. You could try to give them some clues, general clues, maybe how it is being trained, but you cannot give too much details, because basically that is your job, right? So the whole reason that everybody likes YouTube is because of that recommender system, right? So they can't just give it out for everybody to look at or everybody to train, and then everybody, of course, will have their own YouTube. The second level would be global holistic model interpretability. And this just means, how does the trained model make predictions? So you can imagine that this is the access, if you know sklearn, for example, this is having access to the model.fit code. This one is having access to model.predict code. So this one should just tell you how does the model make its predictions. So if it's just a linear model, then you will have a couple of multiplications between some pre-trained weights and your input, give that sum, and there you go, you have your output. So it's a pretty simple one. If it's a neural network, then you will have, just your model, inputs get multiplied with lots of different weights, everybody gets added, you have the neurons, they activate through the, what is it called, an activation function, and that gives you a second layer of, kind of new input that gets the same, well, let's say the same story happening again and again, and that is how you train or how you make a prediction for a neural network. A much more complicated model, as we said, also for the case of like a real company, this level is also extremely impossible to outsource or to provide to people. So interpretability at this scope is very difficult to reach, especially for industrial settings. The third scope, at least, is a bit more interesting, and this one is global model interpretability on a modular level. And this one just only says is, how do parts of the model affect the predictions? So if you are speaking in the terms of linear regression, as we said, it's pretty simple. If your coefficient for that input is very high, that means that feature is extremely important, and that is a very important feature for making the predictions. But if your prediction, if your weight for that feature is, let's say, negative, and it's very big on the negative side, so it's like minus 500 or something like that, that means this feature is very bad for your output, right? So if you are trying to get a loan, this feature is very, very bad, and you should try to minimize it, right? So let's say years of prison. How many years did you spend inside prison? And this is something, of course, we do not want. So probably the model is going to give a very negative value for this one. If we have a coefficient that is extremely close to zero, so let's say 0.001, then that is a coefficient for a feature that the model does not care about, and it's just, not a very important feature to look at. So this is the third level of, or the third scope of interpretability, and it allows you to understand how do the different parts of the trained model affect the final prediction. Now we reach the fourth and the fifth levels, and I believe that these are more realistic levels that you should at least have for every single company. Even if it's like a production level, you should have these two final levels ready for everybody who would ask, right? The first one is local interpretability for a single prediction, or why did the model make a certain prediction for a specific instance? So let's say you go to a bank, you ask for a loan, the bank says, no, I will not give you the loan. It should be your right to ask the bank, why are you not giving me the loan, right? Is it because I am Black? Is it because I am a woman? Or is it just because I am asking, for example, for a house of like 3 million house, and my salary is basically just like 2,000 or barely like the minimum wage, right? So I need like a reason, why did you refuse my loan application? And if that reason is, logical and something that is actionable, something that I can change, then that's something I will just go work on, and then I come back and apply again to your bank, right? So this is the local interpretability for a single prediction. Why did the model make a certain prediction for that specific instance? Going back to the doctor's office, and he's trying to detect cancer, if the model says that this person has cancer, we should ask the model, why do you think that, right? So maybe the model could show you a location in the scan that might look like cancerous cells. So this one is pretty good, and it's pretty easy to provide. As we said, it's just an algorithm. This one is extremely easy. No major losses that might happen to the company. On the opposite, every company should provide you with that. So for example, on Facebook, if you click on any post, you could just click on it and tell, why am I seeing this? There's like this option, why am I seeing this? And they will show you are seeing this maybe because a friend of yours has shared it, or because you were interested in this, and that, or because the model has segmented you into like I don't know, people between age of 18 till 25 who are interested in the Deadpool movie. That's something that you might have been segmented at for, wrong or right. And if you want to get out of it, you can just click exit from this segment of people, and you're never going to see, posts that are related to that segment. So this is pretty important for many reasons. In every single company, you should have it for all the models. And the final one is local interpretability for a group of predictions. And again, this one is extremely important for predicting or detecting biases in the model. So if your model is racist, basically against Black people, this one is the way that you should find that out, right? So if your model is just for like a whole, I don't know, range of different types of people of color, it refused all of them, then something is wrong with your model. So these are, as we said, the scopes of interpretability. And if we go back to the lecture, you'll see them here like summarized. There's a question. Okay. But is it possible to do with any model? For example, this for LLMs, I'm speaking 3, 4 for local interpretability. Absolutely. So we will see later on the model agnostic methods that just work for any model anything outside, right? So it doesn't care what the model is. It works with any type of models. We will also see it during the lab, hopefully this Monday, right? And we will see this happening for like a, not a gigantic text model, so not an LLM, but absolutely not something that is different between, there's no big difference between an LLM and any just random model, because our method is completely agnostic. Just keep in mind that this is not interpretability for generative models. This is interpretability for categorical models, right? So if you have a model that is, for example, classifying a certain novel into whether it is like a romantic novel or this is a book about mathematics, then this is a model, regardless what it is using under the hood, you can interpret its decisions. Thanks, Paulina. That was a great question. So as we said, there are 5 levels of interpretability. 3 levels are highly unrealistic in, industrial settings, and 2 levels which are extremely important to have in every industrial project. The first level is algorithm transparency, so having access to that fit or that train function. Global holistic model interpretability, which is having access to the predict function. And the global model interpretability on a modular level is just having access to the understanding of what different parts of the model contribute to the final prediction of the model. So these are the 3 levels which are a bit difficult to have in industrial situations. The other 2 levels are very simple. Why did the model make a certain prediction for a certain instance? And this one is, why does the model make certain predictions for a certain group of instances, right? So now that we spoke a little bit about interpretability in general and why do we need interpretability and what are the different scopes of interpretability, now let's start with a simple, example of logistic regression. Logistic regression is a pretty simple algorithm, as you guys might imagine. Sorry. Yep. It's a very linear model, right? And it's a simple one. It only has the following. Let me just start typing. Y is equal to ax plus b. Very easy. And then, of course, you will have like a sigmoid function plus like an if statement. If it is above 50% or like 0.5, then you're good. If it's underneath 50%, then you are bad. So it's a very simple model to interpret and a very simple model to understand. So here, if I ask for the following questions, right? If I want to understand the 3rd level, or let's go with the full thing, right? So let's go with algorithm transparency. Do you know how to train logistic regression? Anybody knows how to train logistic regression? Or let's do linear regression, right? Logistic regression is actually a bit difficult with the Newton's, what is it called? Optimization algorithm, but linear regression is an easy one. Anybody knows how to train linear regression?
Just linear where solution is simple line.
Yeah, exactly. So how do you find A and B coefficients?
Usually we have a lot of points from data sets,
Yes,
and
absolutely.
we try to firstly we just define a random line
Yep.
and changing its slopes.
Yep. Absolutely, I agree. Yeah.
Changing its slopes, we're trying to minimize distance from the points.
Absolutely. So there are 2 approaches, right? There's the direct approach, which is just doing the derivations and then finding the actual solution, or there is the what is it called? The how do you say this? The back propagation approach, or the training approach, where you basically start with, as your friend has suggested, with a random set of A and B values, and then iteratively improve those numbers based on back propagation, or even based on just a simple change up and down. If it improves, go in that direction, right? So it's pretty easy solution. There are two major solutions to solve a linear regression task, and all of them are all public. So now we have the algorithm transparency. How does the model make its predictions? The fit, or the predict function. Does anybody know how to make the prediction, right? So if I give you y is equal to 3, x plus 5, and I tell you x is equal to 1, can you tell me what is y?
Yes, just we place our feature x
Yes.
into equation, and it will be x multiplied by 1 plus 5. It will be 8.
Absolutely.
Yeah.
Oh, yeah, congratulations. Thank you so much. So yeah, as you see, we have access to that information, or the fit or the predict function, right? We have access to that, and that is amazing. So it is the second scope of interpretability. Now let's go to the third one. If I ask you the following something, right? The price of the house is equal to 3 times the size plus 100, or let's go minus age, minus 5 times the age of the house, right? So if the house is pretty old, then we are not going to what is it called? We're not going to it's not going to be very expensive. So let's say this is the factorial. Yep. So yeah, so we're not going to go to the third level of interpretability. And if I say the following, how does the feature size influence the actual model's results? Positively, thanks. And how does the feature age? And for a model that we just have no idea what is the size or what is the age, what are we going to give? So for 0, 0, 100, right? So we already have like a certain understanding of what are the different components contributing to the actual prediction. Now let's go to the final one, pretty easy one, which is just if you give me something like y is equal to 8, I should be allowed to understand why did you say that, and the simple reasoning, you just give me 3 times 1 plus 5, and this is the reason. So this is the interpretability level 4, and if it is for level 5, then you would just do that same thing but for multiple people, and you would give them the reason for all of that, right? So as we see, logistic regression, pretty easy algorithm to perform all the 5 levels of interpretability. Now let's go to decision trees, and this one is going to be a little bit less, let's say, less obvious, right? Sorry, let me just do something. Yes. Okay, like that. I actually have very low battery, and that's pretty bad. Let me reduce the, okay, that's good. So for decision trees, this is also another simply interpretable model. We know how it is trained, you know, you have already seen those greedy algorithms, which just take a feature, the best feature at that level, split the data set on like 2 or different directions, and then at each node, you will have to split them again and again and again based on the best feature at that specific level. And that would give you like a hopefully very clean or very I don't know how to homogeneous. Yeah, homogeneous nodes at the end, where the decision becomes pretty fair and pretty direct. So pretty easy how to do the first level, the second level, and the third level. All it's just an if statement. You can understand it. And for the fourth level of why did it make a certain decision for a specific instance, you would just give it the whole branch that led to that decision. So if age above 30 and income under 20 and have 5 kids and something else, then the decision was that, right? So it's pretty easy. You just give it the tree, or not the tree, but like the road that led to that decision for that specific instance. Now, if I ask you the following question, how to change the class of a certain prediction? So let's say this is my tree. This is positive, this is negative, and this is positive. If your client comes to you and says, I was negative here, how can I change that? How can I change that decision? What would you tell the client?
We need to go to the parent node and find why this node decided that it was bad.
Absolutely. So what you should just do is go up from that decision and find the closest positive class and tell them what is the road there, right? So if the closest positive class, for, let's say, for example, here there are 5 options, you tell him what is the option for the positive class, and hopefully he will follow it. So pretty easy to understand and pretty easy to interpret, as we said. Now let's go to the next. So here we could take like a small break, but I highly recommend that we continue, and maybe we like can finish a bit earlier. My battery is a bit down, so let's try to do our best. So what we have seen so far is interpretability, what it is, the importance of interpretability, and the different or 5 scopes of interpretability. We also saw a couple of interpretable models, which are logistic regression or linear regression, and decision trees. Now let's go to our first algorithm for interpreting any model out there, for any a category called model. So any model that is splitting things into categories, classification, or even regression, you are able to interpret that pretty easily with local surrogate or LIME, which is basically local interpretable model agnostic explanations. It's a long name, but you will see that the idea is extremely basic. It's even super stupid how it works very well, right? So we will first see how it works for tabular data, the steps, and a couple of examples. And then we will go for, sorry. And then we will speak about text data and how we interpret models for text data. And then we will see LIME for image data and how do we interpret it for image data. We will do the exact same steps for thank you so much, Paulina. And we will do the same thing for these 3 different levels in the lab. And of course, we will also speak during the lab about GradCam. So LIME, right? What we said about these complex, the simple models is they are very linear and easy to understand. Pretty simple, basic models, right? Unlike, let's say, something like a neural network, which has a very non-linear and complex decision boundary that is very difficult to understand. So if we go, for example, let me just do this really quickly. Do you guys already know this TensorFlow playground?
Kinda, yes.
Yes. Have you experimented? Let me show. Yep. So let's take, for example, this kind of data set. If we use a linear model like this, so this is a linear model. If we use a linear model and we try to train it, you will see that it does not make any good predictions. Linear models are very bad at discerning this one, but they are easy to understand. Whereas something like a complex model with high non-linearities like this, and let's give it ReLU so it trains pretty fast. Yep, like this. And let's try to train. So here you will see that it trains pretty quickly and it is able to find a better solution really fast. So you see, it's doing its best. it will find it pretty quickly. So for this data set, ReLU is definitely not the best algorithm, not the best activation function. Maybe we could have used something like sigmoid. Let's see sigmoid. Maybe it's a bit better. It's a big model though. Let me just try it like this. Yeah, this is enough. This should train fast. Maybe the learning rate also could improve, but this should train pretty fast. Okay, this was not trained very fast. Let's go with a bit higher. Let's see. Oh, for some reason it's not training fast enough. Let's see. Yeah, ReLU is the fastest, at least for live presentations. So let's go with ReLU. Okay. So here's, as we can see in here, for neural networks, the more complicated they are, of course, the learning rate is pretty bad right here. But as you can see, the decision boundary becomes so complex that it's hard to understand why did it make a certain decision, right? If the decision boundary was pretty simple, it's pretty easy to say, right? If it was like a simple decision boundary, you could say, oh, because it was bigger than 5, age was bigger than 5, and weight was bigger than, I don't know, 100. For some reason, it decided that. But when it becomes something very complex like this, the difference between the blue and this one is not something that a human can understand very quickly. Solution: use a very local model. So here, as you can see, when you are looking at this range, the decision boundary is highly complex. But if you zoom in so close, here, for example, you see, in this region, let me just draw something here. Yep. In this region, if we zoom in super close, we can actually see that the decision boundary at a local place becomes actually quite linear, even for a complex nonlinear model. If you zoom in close enough, it will become linear and easy to interpret. And this is the idea, right? The idea is simply to zoom in and estimate why did the model make its decisions, but at a very local level. Here, are the steps for performing LIME, or performing the algorithm of LIME for any tabular model, any model that is trained on a tabular data set. First is you have to select the instance of interest, right? So here, for example, this is the instance of interest, the yellow one. The second is you will have to create new random points around the data set. So for example, if your data set, or if your, if your feature is a categorical feature, then you will have to just play around randomly with the values of that categorical feature. If it's a numerical feature, then it's pretty simple. You just give it any random values, and this will allow you to generate random data sets, right? Random data points. These black points right here are the random points that we will be generating extremely randomly based on the data set that we have. So we don't need even like having access to the data set. All we need is access to the type of the features, and that's it. So here you don't need access to the training data set. You are creating a new training data set randomly. Second, or the third step would be to weight the new models, or these new samples, weight them according to the proximity to the instance of interest. So if you can see in here, these black points, which are super close to our instance of interest, the yellow points are, much bigger, and the ones that are very far away, they're much smaller. Train a weighted interpretable model on the data set with variations. So I would like to just show you an example of what I mean with sklearn linear model, or linear regression. What we mean with this concept of weighted model is pretty simple, right? As you know, you can weight actually your, oh wow, my internet is pretty bad, but let's see. Fit intercept, parameters, Boolean, no. There should be something here called sample weights. Yeah, here it is. Sample weights for the fit function. Sample weights are optional, so majority of your case will not actually be providing them with these sample weights. But if you want, you could provide an individual weight for each sample that will contribute to the loss function. So if that weight of that sample has a high weight, it means it will have a very big importance for the loss function, and it will be very decisive. That specific instance will be very decisive for the decision boundary. Whereas if it has a very small sample weight, it's not going to have that, right? So this is what the weighted linear model actually means. It's pretty simple. All the sklearn models have that concept embedded in them already. So if you have not played with it, I highly recommend trying it at least once for some cases. And then the final one is, instead of explaining the complex model that it has a very, very nonlinear decision boundary, try explaining the local interpretable model. The local linear model that you just built, try explaining that one. So these are basically the steps for performing LIME. It's pretty easy, as we said. Instead of interpreting the global model for all locations and having a single interpretation for everything, now you are building a new small model at a much zoomed in level. You see, we are like zooming in very, very much and trying to build a linear model for that specific instance only to understand what was the reason why the model made its decision at that level. Do you have any questions about LIME?
Oh,
Very clear. Yeah, it's pretty simple algorithm, to be honest. Yeah, it's pretty nice one. So now let's go to LIME for text data sets, right? So LIME for textual data is pretty similar, but instead of having, a feature like age, which has, values like 12, 13, 550 or something like that, now you have actual words. So the solution is pretty simple. You will create a list like this that represents this instance 1, 1, 1, 1, 1, and 1. What does this 1 symbolize? Pretty simply, it symbolizes the fact or the existence of that word, whether this word exists in the sentence or not. So 4 now becomes a feature, and it's a Boolean feature. Is it turned on or is it turned off? So 4 is a Boolean feature. Christmas is also a Boolean feature. Song is a Boolean feature. Visit is a Boolean feature. My is a Boolean feature. Channel is a Boolean feature. And even the wink is a Boolean feature. How do you go to the step 2 of creating or perturbing this new random data set? Pretty simple. Create a data set of ones and zeros, random data set of ones and zeros with the same length. So for example, this third level sentence, 4 does not exist. So it's not a sentence. It's not part of the sentence. So the sentence begins with the following: Christmas, song, visit, my, there's no channel, and then wink. So the sentence that you are sending to your model for actual prediction is the following: Christmas song, visit my wink, right? And here it tells you the probability of it being a spam. Here for these two, the probability was very low. For these two, the probability was very high. For the final one, the probability was pretty low. We will train a model basically on the following data set. So we will train a linear regression on this data set, ones and zeros, right? Pretty easy. And the label will be the following. So the label will be the model's response to that instance. And then we will interpret it as it goes, right? So here we will interpret it as, this is the feature weight for the linear regression. And as you can see, the model does not care about the concept or the feature is, does not care about the feature good, does not care about A, does not care about Christmas or song. What the model really focuses on when it's trying to do spam detection is the word or the feature channel. So channel is a word that is associated with the model, always saying that this is spam. So this allows you to understand, why did the model predict this as a spam, right? This sentence was predicted as a spam. And after doing LIME and creating basically this binary data set and building a linear model on that and interpreting the feature weights, we discovered that the word channel is highly, important for the model to say that this is a span. So this is LIME for textual data sets. It's very slow because, of course, for each one of these black points, you see each one of these black points, we will have to give it a class, whether it's positive or negative. We will have to send it through the model. So we will randomly generate a new data set. This is pretty easy because random generation is very fast. The slow part would be to send, I don't know, let's say 1,000 new samples through the model. If it's a CNN, then you will have 1,000 classifications through the CNN, just so you can build this binary data set. Because for each sample, you will have to send it through the model and get the probability of that class from that model, right? So it's a very slow algorithm, but it performs pretty well. How can we do it for images, for example? So for text, simple, we turn off a word or we turn it on, right? So either we keep the word Christmas or we don't keep it. It's a binary thing. For images, how do we do that? It's a very simple technique called superpixeling. So what superpixeling does is just combines different pixel regions based on similarities on pixel values, right? So if so here, for example, this is snow, it has the white color and they are close together. So we will group this whole region together as one single region. And when we are trying to perform LIME, we either turn that region on or turn that region off and generate different types of pictures. And through the linear model, we will be able to understand what is the part of the image that made the model make that decision. So here, for example, we will see why did the model make that decision for that specific instance. If we go back to the first of the lecture, to the start here, this result is generated by LIME. And if we see the regions that the model is looking at, clearly the model is not looking at the horse to make its decisions, but looking at the castle and at the sand and at these regions, or for example, here are the palm trees, to say that this is an Arabian camel and not a horse, right? So through LIME, we're able to interpret this computer vision model and understand what are the regions inside the image that made the model make a certain prediction. So here, as we said, we apply superpixeling, create these perturbed instances which contain only some parts of the image. If the picture is classified as positive, then the model is going to learn from that this is this region is very bad for it, or this region is the reason why we made that prediction. So this is it for LIME. Do we have any questions about LIME in general? I didn't quite, what is superpixel? So yes, we're not going to go into what superpixeling is.
Sorry.
We will, yes?
My question about interpretability versus explainability.
Okay.
What's the difference between it? As I understand, explainability, it's more lower level than interpretability. Is it true? And if is it true, what it means? Yes.
So yes, so an explanation usually is why did the model do a certain prediction for a certain group of people or for a certain level of people, right? So here, when we go back to the scope of interpretabilities, or at least that's my opinion, right? So the scope of interpretability, so for example, the scope number 1 for interpretability or algorithm transparency, this is not an explanation, right? So this explains nothing. When you're asking for an explanation, you're most likely speaking about these final 2 levels of interpretability. This is where explanation becomes important, because this is the region where you are speaking with a normal human being and no longer an expert. For algorithm transparency, if you are going to provide like the transparency for your algorithm, then your algorithm, the code for it can be as complicated as possible, right? Your Netflix, your recommender system might have millions of lines of code just to have the recommender system. So algorithm transparency or the interpretability in here is not an easy thing to understand for a human being. But at the last two levels, local interpretability for a single prediction or local interpretability for a group of predictions, these two must be extremely easy for a human being to understand, because these are explanations, right? So explanations for me are something that is extremely easy to understand by a human being. Interpretability contains explanations plus things that only experts can understand.
Okay. I have a question about a local interpretability of scope of interpretability for group of prediction. Is it a global interpretability or not?
Can you go back to, can you do it again, please?
Okay, when you show some scope of interpretability for single, yeah, here, yeah. What the next point 3.3.5, yeah, a local interpretability for a group of prediction. It is a global interpretability.
No.
Or
So yeah, this one depends on what algorithm you're going to use. We're not going to check any algorithms for local interpretability for a group of predictions, but it depends on basically how you're going to build it. But this is not something that is global for the whole complex model to understand. This is very localized to a certain part of the model. So let's say this is localized to a certain feature, let's say race, or it's localized to a certain, feature like gender or income or something like that, right? So it represents a very local part thing of the model. It's not something that is global to the model itself, but it's a very localized interpretability thing. Even if it's not for a single prediction, but for a group of predictions, this group of predictions will have something in common, right? So these are like quality pictures, which are very bad, maybe, or maybe let's say a type of group that is, as we said, a certain gender or certain category. Things like that. Yep.
Okay, thank you.
Makes sense? Perfect, thank you. And for super pixeling, as we said, we're not going to discuss super pixeling a lot. It's just that ability, you can think of it as an algorithm, just merges different pixels together and creates a region in the image that you could just turn off, meaning you could set its pixels to 0, or you could turn it on, meaning you will keep its pixels. We will talk a lot more in detail about it during the object detection algorithms part, when we are speaking about the lecture of object detection, because super pixeling, or at least the other version of it, which is, I forgot, local search. I forgot the name of it, but basically for object detection is extremely important because it groups different parts of or different pixels of the image together, and that allows you to get like a certain understanding of what are the objects in the image to make what is it called, like the prediction about the location of the object, right? Or to propose regions for your object detector later on. So for super pixeling, I know it's a bit unclear how does it work right now. It's a very simple greedy algorithm that combines pixels together based on pixel value. If the pixel values are similar, it will group them. If they are not similar, then it will create another group or another region, right? So it's a pretty simple algorithm. No need to go into detail about it. Are you guys, does that answer your question? Okay. If it doesn't answer your question, then don't worry. By the next lecture, which is going to be about object detection, we will speak so much about it in detail, and hopefully you will understand it a lot better. So far we spoke about different types, different topics. So as we said, what is interpretability? Why do we need it? What's the importance of it? And what are the 5 scopes of interpretability? The 3 scopes that are very unrealistic for for companies and for industrial settings, and the two scopes which are extremely important for companies in industrial settings. And then we spoke a little bit about interpretable models in general, such as logistic regression, linear regression, and decision trees. And we spoke about LIME, which simply creates a linear model at a very localized region. And LIME does not need access to the training dataset. It creates a new dataset randomly, only looking at the feature types instead of looking at the actual training dataset. And as we said, it just trains a simple linear model and interprets that simple linear model instead. So it's a very simple idea. Now, GradCam, on the other side, is much more beautiful idea. So it's a little bit more complicated, but again, it is so basic and it's so simple, the idea, that it's so stupid. How does it work? And how does it work so well also, right? So GradCam is a very popular technique for creating class-specific heat maps based on a particular image, trained CNN, and a chosen class of interest. So let's look at it. So this is the actual results of GradCam. So as you can see, since it does not use superpixeling, its results are not super linear. They are much like, a heat map, as we said. So here it tells you, for example, these are the reason why we made the decision that this is a dog. Now, let me ask you a question about the last week's lecture, right? If we go back to last week's lecture, we saw something that is similar to this in the last week's lecture when we were speaking about CNNs. We saw something similar to this. Do you remember it?
Yes, kind
Input
of.
image, CNN layer, and then this one is?
Sorry, can you repeat your question?
So we saw yesterday, last lecture, we saw something similar to this image with like black background and some pixels turned on like this. And convolutions. What is it called?
Filter?
Convolutional feature maps. So let me see.
Activation map?
Yes, the activation map or the convolutional feature map or the output of our CNN, right? So the CNN looks at the image and then it performs some calculations using the kernel and the output. Let's go back to the lecture and look at it, right? Let's see it together.
Okay.
For some reason, I'm having some issues. Can you guys send me the link to the lecture?
嗯
Oh, wait. Here, yeah. Let me just
If you mean about your screen, no.
Okay, I have it. Let me share the screen. There we go.
Nice. Yeah.
Here, during this video, you see there's the image, and here is the calculation happening. You see this? This
Yes.
is the output of the CNN. Each layer, each convolutional layer will give us this output. This is the convolutional feature map, you see? Some pixels are green, some of them are turned off, and some of them are red. Let's go back to our lecture, and here we can see the same pattern again. And this is exactly it, because we're actually looking at the same thing. What GradCam does, very simply, is the following. Takes an input image like this. You see there is a cat and a dog at the same image. Sends them through the CNN. And this gives you the rectified convolutional feature maps. Call them convolutional feature maps. Call them the output of the CNN. Call them the activation feature maps. Call them the embeddings. You can call them whatever you want. They remain to be the same concept, right? This is the output of the convolutional layers. What you will do is you will combine these layers like this, these couple of layers, you will combine them to create a single layer like this that we call the interpretation of the model. Very important thing is how do we combine these layers? Remember the kernels that we spoke about last week? We said that each kernel is trying to learn something specific. So for example, at the same layer, one kernel is trying to look for the nose, another kernel is trying to look for the eyes, another kernel is trying to look for the mouth, another kernel is trying to look for the hair. So we have different kernels looking for different things. Here in this situation, we have a kernel looking for cat face, a kernel looking for dog face, a kernel looking for I don't know, a human, and other kernels which are looking for different concepts. So combining these convolutional feature maps together at the same time like that, just randomly, will result in a very unreadable explanation, right? It's still an explanation, but it's very hard to explain. This is why we need the final step of the GradCam. Very simply, we go through the category or the classification step, right? So here what we will do, we will go through the classification. We have the classification as a tiger cat. Thank you so much. Somebody sent for deeply understanding. Let me see. Oh, thank you so much. Yeah, that's a great link. We will look at it later on. So let's go back here and take a look at it. So we will take this class, a tiger cat class, and what we will do, very simply, because thanks to PyTorch, we have access to it. Remember, we said that last week. We have access to the derivatives of this class with regards to these convolutional feature maps. It's a very simple thing to access through PyTorch. We will see that later on in the lab. But basically, this tells you how much did this convolutional feature map influence the prediction of tiger cat. If this convolutional feature map was very important for the prediction, it will have a lot of, high gradients in here, like 5, 10, 500, something like that. If it was extremely useless, then it will have a very, zero-ish numbers. And if it was very negative, very bad for that category, then it will have negative numbers. So this is what we get. What we will do is simply take the average of that gradient for that convolutional feature map. So we will take the average for this blue gradients. As you know, for each single output, we will have a gradient. So here for each one, we will have another matrix. This is matrix of gradients. We will take the average of this matrix, and that will give us a number that says this convolutional feature map was important for the prediction or it was not important, right? Afterwards, we will combine these convolutional feature maps together and combine it through just a summation, multiplication and summation, pass them through the ReLU so that we ignore those negative negative contributors. So we ignore them, we keep only the positive contributors, and that gives us the actual GradCam interpretation. So as you can see in here, as we said, this interpretation is only a combination of the convolutional feature maps from the CNN. How do we do that combination? In a linear manner, we get the weights through the help of PyTorch. We get the gradients of that specific category, let's say a specific class like tiger cat, a human, or a dog, with regards to those convolutional feature maps. That gives us a matrix of gradients. We take the weight for that specific convolutional feature map. We can revise the steps here together. The GradCam steps are pretty simple. Compute the gradients of YC, the class C, with respect to the feature map activations, AK, of a convolutional layer. We can choose any convolutional layer, preferably the last convolutional layer that we have, because that one is usually the highest level of abstractiveness, or that provides the best interpretations, because the lower level layers are mainly focused on lower level features such as the eyebrows and stuff like that, whereas the final layers are interested in the whole category of, or the whole range of objects that we have, right? Calculate the alphas basically by simply taking the average and then calculate the final GradCam heat by performing a weighted combinations of the feature map activations with the weights, which are just the alphas that we calculated, which is the average of the gradients. So this is it for basically for interpretability. As we said, it is a pretty simple lecture. Do you guys have any questions?